Look at this monitor. SpO₂, 96%. Blood pressure, 118/72. Heart rate, 90. Every number is green. If you glanced at this monitor from the doorway, you'd move on to the next room. Here's the problem. The patient's hemoglobin is 8.5. And once you run the math, the actual oxygen this patient is delivering to their tissues right now is running well below normal, roughly half. Nothing on that monitor told you that. The pulse ox can't see it. The blood pressure can't see it. You need one more number and one equation to find it. That equation is DO₂, oxygen delivery. By the end of this lesson, you'll be able to look at a normal set of vitals and know in seconds exactly what else you need to check. This is HEMO4. You already have cardiac output from HEMO2, how much blood the heart pumps, and you have pressure isn't perfusion from HEMO1. This lesson is where those two ideas cash out into a number you can actually calculate. How much oxygen is reaching the tissue per minute? Start with 1 unit of blood. How much oxygen does it actually carry? That's arterial oxygen content, CaO₂. CaO₂ equals 1.34 times hemoglobin times SaO₂, the oxygen riding on a hemoglobin, plus 0.003 times PaO₂, the small amount dissolved directly in the plasma. 1.34 is a constant. How many milliliters of oxygen 1 gram of fully saturated hemoglobin can carry? 0.003 is a different kind of constant. How little oxygen plasma can hold on its own per millimeter of mercury of PaO₂. Notice already, one of these numbers is over 400 times the other. Keep that in mind. Let's work it on a different patient. Hemoglobin is 9, SaO₂ is 92%, and PaO₂ is 70. Don't worry, we'll come back to the one from the cold open. The hemoglobin term, 1.34 times 9 times 0.92, that's 12.06 times 0.92, 11.1 milliliters of oxygen per deciliter of blood. The dissolved term, 0.003 times 70, equals 0.21 milliliters per deciliter. Add them. CaO₂ is 11.3 milliliters of oxygen per deciliter of blood. Look at what just happened. 11.1 came from hemoglobin, and 0.21 came from dissolved oxygen. Hemoglobin did essentially all of the carrying, about 98% of the total. That dissolved sliver barely moves the number at all. Pearl. Hemoglobin does almost all of the carrying. If so much oxygen delivery is in question, check the hemoglobin before you crank the FiO₂. Pause and predict. Quick one. This same patient's PaO₂ jumps from 70 to 100. A real, meaningful improvement on an ABG. Pause it. Does CaO₂ change a little or a lot? A little. Remember, 0.003 times 100 is 0.3 up from 0.21, a gain of 9/100ths of 1 ml per deciliter. You'd barely notice it in the equation, and you won't notice it at the bedside either. We'll come back to why that matters in a minute. CaO₂ tells you how much oxygen is in each deciliter of blood. It doesn't tell you how much oxygen reaches the tissues per minute. For that, you need to know how much blood is moving. That's cardiac output from HEMO2. Multiply the two together and you get DO₂, oxygen delivery. DO₂ equals cardiac output times CaO₂. Cardiac output is in liters per minute. CaO₂ is in milliliters per deciliter. So we multiply by 10 to make the units line up. DO₂ comes out in milliliters of oxygen per minute. For the hemoglobin 9 patient, CaO₂, 11.3. Let's say the pump is completely fine, cardiac output 5 liters a minute, right in the normal range. 5 times 11.3 is 56.5 times 10. DO₂ is 565 milliliters of oxygen per minute. Normal DO₂ at rest runs around 1,000 milliliters per minute. That patient is at 565, a 43% drop. And the pump is normal. The pressure would look normal. The heart rate might look normal. The only two things wrong are the hemoglobin and a mild dip in oxygenation. Multiplied together, they cut that patient's oxygen delivery almost in half. That's the payoff of everything HEMO 1 and 2 built. Pressure isn't perfusion, and now you can see exactly why. DO₂ has a third ingredient. Neither of those lessons cover. Now, go back to the patient from the cold open. Hemoglobin is 8.5, and the ABG came back with an SaO₂ of 96% and a PaO₂ of 80. 1.34 times 8.5 times 0.96 is 10.93 plus 0.003 times 80, and that equals 0.24. CaO₂ is 11.2. Normal pump again, cardiac output at 5. DO₂ is 559 milliliters of oxygen per minute, about 44% below normal. Different numbers, same story. And that's the patient whose monitor is all green. Pitfall. A reassuring SpO₂ and a reassuring blood pressure can both be true at the same moment. DO₂ is cut nearly in half. Don't let two normal numbers wave off a low hemoglobin. Pause and predict. Back to the hemoglobin 9 patient, the one we worked first. SaO₂ is 92%, PaO₂ is 70, cardiac output a normal 5, DO₂ is 565. Pause it. Which single change gets you more oxygen delivery? Pushing SaO₂ to 97% and PaO₂ to 100 with oxygen, or transfusing hemoglobin up to 12. Push oxygenation first. SaO₂ 92 to 97, PaO₂ 70 to 100. Hemoglobin unchanged at 9. CaO₂ becomes 1.34 times 9 times 0.97 plus 0.003 times 100. 11.7 plus 0.3 is 12 milliliters per deciliter. DO₂ is 5 times 12 times 10, 600 milliliters per minute. A gain of only 35 milliliters per minute over baseline, about 6%. Now, transfuse instead. Hemoglobin 9 up to 12, SaO₂ and PaO₂ unchanged at 92% and 70. CaO₂ becomes 1.34 times 12 times 0.92 plus 0.003 times 70. 14.79 plus 0.21 is 15 milliliters per deciliter. DO₂ is going to be 5 times 15 times 10. 750 milliliters per minute. A gain of 185 milliliters per minute. About 33%. Same sized effort on paper. One lever moves DO₂ by 35, the other moves it by 185, roughly 5 times further. In this specific comparison, once the patient is reasonably saturated, chasing PaO₂ higher gives you almost nothing extra. The hemoglobin term already dominates the equation, and the dissolved term was never big enough to matter. Hemoglobin and cardiac output are usually the higher yield levers. Real transfusion decisions weigh risk and benefit well beyond this math, but the math tells you why the conversation happens at all. Exam tip. Choice between increased FiO₂ and transfuse for a hypoxic but saturated anemic patient. The math says hemoglobin usually wins. Know why, not just the answer. One more piece. DO₂ isn't the whole story. The body also consumes oxygen, VO₂, roughly 200 to 250 milliliters per minute at rest. Divide VO₂ by DO₂, and you get the extraction ratio, about 20 to 25% normally, over a wide range. If DO₂ drops, tissues just extract more of what's left. VO2 stays flat, and you can't see the trouble on a vital sign. Push DO2 low enough though, and extractions run out. VO2 starts falling too, and that's where lactate begins climbing. SvO₂ and ScvO₂, venous oxygen saturation, are how you watch this at the bedside. Falling SvO₂ with stable demand usually means falling DO₂ before anything else on the monitor moves. At the bedside, a normal SpO₂ tells you almost nothing about DO₂ without a hemoglobin next to it. Trend SvO₂ or ScvO₂ and lactate when you're worried about delivery. They see the problem before vital signs do. One more time, fast. CaO₂ is hemoglobin times SaO₂ times 1.34, plus a nearly invisible dissolved term. DO₂ is that content times how much blood the heart moves times 10. 3 levers: hemoglobin, oxygenation, and cardiac output. And hemoglobin usually gives you the biggest move. A normal SpO₂ and a normal blood pressure can both sit on top of a DO₂ that's nearly cut in half. 1. Hemoglobin 9, SaO₂ 92%, PaO₂ of 70, cardiac output of 5. What's the CaO₂? And what's the DO₂? 2. Why does raising PaO₂ from 70 to 100 barely move CaO₂, even though it looks like a big ABG improvement? 3. A patient's SpO₂ is 98% and steady, but their SvO₂ drifts from 70 to 52% over an hour with no change in activity. What does that suggest? Answers are pinned in the comment. Next on the map, we head into ABG interpretation and the vasoactives that actually move these levers on purpose. I'll see you there. There's a free one-page study guide linked below. Hit subscribe and you'll catch the next one. I'm building these in order so they stack.